Okay, so we have Camilo Arias Abad from the Universidad Nacional de Colombia in Medellin, and he will give a talk titled Singular Chains on Lie Groups, the Cartan Relations, and Chern-Weil Theory. Thank you.
All right. Well, thank you. Thank you so much, Manuel, and the organizers of the seminar for the invitation to speak. It's a pleasure to talk to you. That's the title of my talk, Singular Chains on Lie Groups, Cartan Relations, and Chern-Weil Theory. This is based on joint works with my colleague and friend Alexander Quintero, who also works here in Medellin. All right, so here's the outline of the talk. So I want to divide it in 3 parts. The first part will be about singular chains on Lie groups, on the Cartan relations, as the title implies. Then I'll speak about Chern-Weil theory and what happens when the Lie group is compact. And then I will explain how the results of the first 2 parts are related to the theory of higher local systems on classifying spaces. That's the plan. But I also wanted to say, if anyone has questions or comments or corrections during the talk, please feel free to interrupt. All right, so that's the plan. So I will start with the main object we'll consider in the talk, which is the space of singular chains on a Lie group. So we fix a simply connected Lie group with Lie algebra G. And sorry, this maybe is too small. Let's see. Right, so we fix a Lie group G, which we'll assume to be simply connected. It's not strictly necessary, but it makes the statements easier. And we'll consider the space C of G of singular chains on G. So by this I mean the space of smooth singular chains on G. So just smooth maps from a simplex to G. And the vector space spanned by that. And so this space has the algebraic structure of a Hopf algebra. In fact, it's a differential graded Hopf algebra. So what this means is that it has a product and a co-product. So you can multiply things and you can co-multiply things. That's what being a Hopf algebra means. And the product and the co-product, they are not independent of each other. They are related, and the relationship is given by this. So that is the algebraic structure that is present in the space of singular chains on Lie group. Let me remind you, because maybe not everyone is familiar with this, how these structures are constructed. So the fact that it's a co-algebra it does not depend on the group structure. It's just because the chains on any space are a co-algebra. But the fact that it's an algebra depends on G being a group. So the multiplication is defined as follows. I'll call this multiplication mu. And is the composition of 2 maps. Is the composition of the Eilenberg-Zilber map with the map induced by the multiplication on singular chains. So the map induced by multiplication is just where you use the group structure, but the Eilenberg-Zilber map is something combinatorial. And it's defined as follows. This is the multiplication map, but then you have the Eilenberg-Zilber map, which is defined by the following formula. You have 2 simplices on G, and you should be able to multiply them. And this is the formula. This chi is some permutation that I will explain in the next slide. So, so let's see. Right, so the Eilenberg-Zilber map is really a combinatorial map, as I said, and it depends on the fact that a cube of dimension n can be divided into n factorial simplices, just because there are n factorial possible orders for the coordinates. So since you have a cube and you can divide it into n factorial simplices, then that combinatorics produces the formula for the Eilenberg-Zilber map. It just tells you that you have a map from a simplex of dimension r plus s to a product of 2 simplices, one of dimension r and one of dimension s. And this map is just given by the permutation. But geometrically, it simply comes from the fact that you can divide a cube as n factorial simplices. And that's the formula that induces the Eilenberg-Zilber map. So you have this differential graded Hopf algebra of singular chains on G. And I want to state the first problem I want to discuss, which is the following. We consider this algebra of singular chains on G, and this is a differential graded Hopf algebra in particular. It is an algebra, and it has a subalgebra, which is the algebra of zero chains on G. The algebra of zero chains of G is just the group ring of the group, right? So I want to think of this algebra of singular chains on G as some sort of an extension of the group ring of G. Now, for the group ring of G, you can consider the modules over the group ring of G. And of course, the main point of Lie theory is that the modules over the group ring are the representations of the group. And the point is that you can describe these representations infinitesimally, right? So the correspondence between the Lie groups and the Lie algebra is the fact that this, that everything about the group, in particular the representations, can be described infinitesimally in terms of the Lie algebra. But now if you look at this diagram, there is a question that you can ask, which is, well, I know how to describe infinitesimally the representation of this.
I'm sorry, these are representations as a discrete group, though.
I want to consider smooth. No, right. So I'm considering sufficiently smooth representations, right?
But when you say it's the group ring only makes sense for discrete groups, right?
Well, you can just formally construct the group ring, forgetting about the smooth structure, and then consider a subcategory of modules, which are those that are sufficiently smooth. But
those would not be equal to like smooth representations. They're the same as representations as a discrete group.
No, right. But then inside of that, you can restrict to the category of representations which are sufficiently smooth. That's what I mean.
But then the two would not be equal, right? I mean,
that would be different, right? Okay, so maybe I should, when I write modules, so in all this talk, whenever I write modules, I should say smooth modules. So there is some adjective that I need to put there, where I consider things that vary smoothly with respect to the structure. That's right, but you're completely right. So when I write mod here, I'm omitting some details, which is that I need to assume that the algebraics, that everything varies smoothly with respect to the parameters. That's right. Thank you. Okay, so if you look at this diagram, you say, well, I know how representations of this can be described infinitesimally in terms of the Lie algebra. And the question I want to discuss is, if you want to look at modules not only of C0, which is the group ring, but of the whole algebra of singular chains, what is the corresponding infinitesimal description of this category of modules? That's the question I want to address. So I want to describe infinitesimally the modules over this. Can be described infinitesimally. Right, that's sort of the question. Okay, so let me, the answer to the question comes from the Cartan relations, which are probably familiar to most of you, which is the following. When you have a finite dimensional Lie algebra G, or in general any Lie algebra, you can define a new differential graded Lie algebra associated to G, which is, I will denote it by TG, and it's defined as follows. So as a vector space is just generated by two copies of G, one in degree 0 and one in degree -1. And the commutators are given by what are called the Cartan relations. So it means that the copy in degree 0 is just G itself. The copy in degree -1, well, the bracket with itself has to be 0 just by degree reasons. But the bracket between something in degree -1 and something in degree 0 is also given by the bracket in G. And this has a differential which sends something in degree -1 to the corresponding element in degree 0. So these relations are usually called the Cartan relations. And they come from...
Can you quickly say L is in degree 0 and iota is in degree -1, or the other way around?
That's right. L is in degree 0 and iota is in degree -1. That's right. Thank you.
So D goes up in the differential.
Right. I'm using conventions in which all differentials are cohomological. So in particular, the singular chains are concentrated in negative degree.
So this differential grade Lie algebra is quasi-isomorphic to the 0
That's
differential
right.
grade Lie algebra.
Intractable. That's right. That's right. So this differential of iota v is LV. And this is a contractible differential grade Lie algebra. That's right. Okay, so where do these relations come from? Probably most of you recognize it from differential geometry. It's the following fact. If you have a Lie group G which acts on a manifold, then the Lie algebra of the Lie group acts on differential forms in the manifold by Lie derivatives, but it also acts by contraction on differential forms. And this action by Lie derivatives and by contractions, they satisfy some relations, and these relations are precisely the Cartan relations. So this comes from differential geometry. It's just the relationships that exist between Lie derivatives of vector fields and contractions of vector fields. These are the Lie algebra that I described, TG, is simply the universal Lie algebra that satisfies the Cartan relations. Now, the first theorem I want to mention is the following theorem: is that the category of representations of this Lie algebra TG is naturally equivalent to a category of modules over the algebra of singular chains on G. So this should be thought of as an extension of the usual theorem that the category of representations of the Lie algebra is the same as the category of representations of the Lie group, which is the representations of the group ring, modules over the Lie group ring. And here, as Mahmoud said before, I'm hiding some adjectives. So here, this word mod should mean sufficiently smooth modules over this algebra. So here, there's something hidden which is sufficiently smooth.
Camilo, question.
Yes.
Is this mod the category of modules of the chains on G? You mean, I guess, DG modules?
DG modules, right.
But it's considered as an ordinary category.
Right, so for now, this first theorem is about an ordinary category.
Okay.
The second theorem I want to mention is I want to see what happens when G is compact. You can promote this theorem to an equivalence of DG categories, an infinity equivalence of DG
strict equivalence.
This is a strict equivalence, that's
Okay.
right. For now, I'm just considering this as a category. Then I will enrich it to make it a DG category and see that in the compact case, you can promote the theorem to a theorem about DG category. Okay. That's right. But so far, this is just an ordinary category. And the statement here is that if you have a representation of this Lie algebra, of this differential graded Lie algebra, you can, out of this, promote it to a module over this algebra of singular chains. That's sort of the statement, and that this procedure is bijective and natural.
And that category of modules is also the same as the category of infinity representations of G on chain complexes?
No.
No, because
no, that's something else. No.
I think he's considering this as an ordinary category and not the DG category.
That's right. Yeah.
Okay.
I think what maybe I will say more about this later, but I think topologically what the right way to think about it is as local systems on the classifying space of G, at least in the compact case. But I will say more about it in a moment. But for now, I want to tell you how the proof works of this theorem because it's very explicit. So what is the question? So in some way, I need to produce a module over this algebra given a representation of this Lie algebra, right? So it's an integration procedure as you do in Lie theory. And so I start with a representation of this Lie algebra TG. And somehow I need to produce a module. So I can give you an explicit formula for the module. And it's the following. You fix your Lie algebra G. It has a group G that corresponds to it. And this group is simply connected. That's important because I want to integrate ordinary representations. And so the claim is that given this representation rho, I can produce in a natural way a sequence of differential forms in the Lie group G with values in endomorphisms of B. So each of these alpha i's are differential forms in G with values in endomorphisms of G, and they are characterized by the following property. When you evaluate these differential forms at the identity, they're given by a sequence by iterated application of the representation rho. So if you restrict this differential form at the identity, what you do is you apply rho to the first one, then rho to the second one, and so on. Now, this doesn't look antisymmetric, right? This doesn't look like it defines a differential form because it doesn't appear antisymmetric. But if you look at the axioms for the algebra TG, they precisely, one of them tells you that this is actually an antisymmetric expression. So it defines a differential form at the identity. And then if you require additionally that this form be equivariant with respect to the action of G, then it extends uniquely to a differential form in the Lie group G. So this property that it restricts by this formula the identity and it's equivariant completely determines a differential form alpha, which is the sum of the alpha case. Now, this differential form alpha that I just defined by these properties satisfies the following conditions. It satisfies these three differential equations. These differential equations, well, this relates the differential form with the action of the Lie algebra. The second one tells you how it behaves with respect to multiplication on the group. And the third one tells you that the two differentials that you have in the Lie group are related. And so starting with the representation of TG, you construct a differential form satisfying these equations and being equivariant. And now once you have such a differential form, what you can do is you can integrate it. So you define something that behaves like the ordinary, the Rham map, right? You take a differential form and you view it as a cochain by integration over the simplex, and that gives you an endomorphism of V. So this map is something that you give it a simplex and it produces an endomorphism of V. And the theorem is a claim that the properties of this differential form, the differential equations that this differential form satisfy, are precisely the conditions required for the map I to be an algebra map. So it defines a module structure on V. So V is a module over this algebra. So that's the functor. So that's how you produce modules given representations of the Lie algebra. And now the claim is that this correspondence is bijective. In other words, that if you have any module that's sufficiently smooth, in the sense that things vary smoothly with the parameters, then it's going to be constructed in this way. So these are all just like Lie theory, right? So that's the first theorem. And of course, I require that the group G is simply connected because I need to use extend the form equivariantly by the adjoint action, and that's something I can only do if I assume that the group is simply connected. If it's not simply connected, I can write some other statement, but this is the interesting case anyway. All right, so that's the first part of the first construction I wanted to mention. Now I want to continue by mentioning what's special in the case when the Lie group is compact. So in the previous discussion, there was no compactness assumption on the Lie group, but I want to explain that in the compact case, this construction is special and it relates to Chern-Weil theory of characteristic classes. So I want to explain how that works. So let me just very briefly remind you about Chern-Weil theory of characteristic classes. It's just a way to construct characteristic classes of principal or bundles in terms of differential geometry. So you start with the principal G bundle over X, And this principal G bundle is classified by a map to be G. And because it's classified by a map to be G, it induces a morphism in cohomology, like that, from the cohomology of BG to the cohomology of X. And the characteristic classes are the classes in the image of this homomorphism. Now, I want to describe how you can sort of geometrically, in terms of the geometry of Lie theory, you can construct a geometric model for this characteristic homomorphism. So you start with the Weil algebra of the Lie algebra G, which from the point of view of this talk can be defined as the Chern-Weil-Eilenberg complex of the Lie algebra TG. That's not the way it's usually described, but it's isomorphic to it. So it's just, as mentioned before, because TG is a contractible Lie algebra, then the Chern-Weil-Eilenberg complex of it, it's also contractible. So the Weil algebra is a contractible differential graded Lie algebra. And it should be contractible because it is to be thought of as differential forms on EG, on the total space of the universal bundle for G, which is of course contractible. So it makes sense that the Weil algebra is contractible. Now, the point is that if you think that the Weil algebra behaves as differential forms on EG, then its basic part should behave as differential forms on BG, and in fact it does. Turns out that if you compute the basic part of Weil algebra, you get the invariant polynomials of the Lie group. And the invariant polynomials in the Lie group is precisely isomorphic to the cohomology of BG. This is in the compact case. So this computation is an infinitesimal description of the cohomology of BG in terms of the Lie theory of G. Now, Chern and Weil did more. They not only described the cohomology of BG, but they described also a formula for the mapping cohomology. I'm sorry. I'm sorry. There was some noise. All right. So I said this computation tells you what the cohomology of BG is, but you want more. You want a model for the map in cohomology, and that's what Chern and Weil described. So you can describe an explicit map from this basic part of the Lie algebra to the cohomology of G in terms of the curvature of a connection, and this is what's called the Chern-Weil homomorphism. And this is in terms of the curvature of a connection. Okay, so all right, so I'm sorry, there's some noise, but we have a baby. All right, so this is what I wanted to say about Chern-Weil theory. Now I want to explain how this Chern-Weil theory is related to the story I told you before about the representations of the Lie algebra. And it's what Manuel mentioned before, this category of representations of TG. Well, in principle, I was considering it only as, thinking of it only as an ordinary category, but it has a natural enhancement to a DG category. So DG category simply means that the home spaces are not just sets, but they are chain complexes and everything is linear. So that's what a DG category is. And this rep of TG admits a natural enhancement into a DG category that I will denote rep over line TG. And what's the difference? The difference is that when I take, if I have two objects here, if I have, let me see. Yeah. If I have two objects, say V and W, are objects in rep of TG, then I can construct a chain complex of morphisms between them, which is going to be home in rep of TG over line from V to W. That's going to be, well, you tensor with the Weil algebra, you do the ordinary home, and then you take the basic part of this. And that's a chain complex. And this chain complex is what we're denoting by home rep over line G. So this is the natural way to enhance this category so that it becomes a differential graded category. Now, similarly, the category of modules over C of G, which we were considering simply as a category, can be enhanced to make it a DG category also. And the way you enhance it is you use Hochschild cohomology. So as before, if you have two objects here, V and W, which are objects in the category of modules of C of G, then you can construct a chain complex of maps between them, which is what one would denote home in sorry. Right, so if you have two objects in this category, you can construct a chain complex of morphisms between them as follows. Take mod of C of G bar of these two objects, and this is just the Hochschild complex, Hochschild cochain complex of the algebra of singular chains on G with values in home, VW. Right, so the point is that because V and W are modules over singular chains, and singular chains is a Hopf algebra, then the home space is a bimodule over singular chains, and you can consider the corresponding Hochschild cochain complex. And this is what we will consider as the space of morphisms between V and W in the category mod bar. Okay, so the theorem that I want to mention is that in the compact case, you can sort of promote the first theorem I mentioned about the equivalence of category to a theorem about equivalence of DG categories. And this is what I proved with Alex. So this is with Alexander Quintero. So we fix G, a compact simply connected Lie group with the algebra G. And then you have the following DG categories are naturally A-infinity equivalent. So they cannot be related strictly by, well, the way we constructed it is we constructed a zigzag of infinity equivalences. So I will say something about the proof in a moment, but for now, the idea is that this category is rep of TG with overline, meaning that it is enhances DG category, and mod overline, which means that you consider it as a DG category. They are A-infinity equivalent in the compact case. Notice that compactness is something that you should expect because the Chern-Weil homomorphism, the infinitesimal description of the Chern-Weil homomorphism is something that only works for compact groups, right? So you only expect to have this equivalence of DG categories when the groups are compact. Somehow, in the non-compact case, you cannot reduce to infinitesimal computations because the invariants do not behave well in the non-compact case. So that's the theorem. So I want to tell you how the proof of this theorem works, what are the ingredients that come into it, and how it relates to other things. So let me tell you what the ingredients for the proof are. The first ingredient is the theory of Chen's theory of iterated integrals, which I will say something about in a moment. The second ingredient is Gugenheim's A-infinity version of the Rham's theorem, which I will also say something about in a moment. Then I'll say something about the Bott-Shulman algebra, the Bott-Shulman-Stasheff algebra, and the non-commutative version of the Weil algebra, which was constructed by Alekseev-Meinrenken. These are sort of the key ingredients in the proof. So let me tell you what the sketch for the proof is, and then I'll tell you how these ingredients enter into the proof. So the proof is, well, you need to construct an equivalence of these two categories. So you have rep bar of TG somewhere here. And on the other corner, you have this category of modules with bar over C of G. And what we did is we consider some intermediate categories, which I will call maybe A and B. So this is B, and there are functors between them. So this is an A-infinity equivalence. This is an equivalence, and this in this direction is an equivalence. So the way we prove that these two categories are A-infinity equivalence is because we construct two intermediate categories and then relate them by a zigzag of categories. Now, the ingredients that I just mentioned in the proof, they enter in this diagram as follows. This part uses the A-infinity, the Rham theorem. This part uses the Bott-Shulman-Stasheff algebra. And this uses the Alekseev-Meinrenken. This uses Alekseev. So these are just words for now. So let me just tell you what these words mean. So let me just tell you what these ingredients that I mentioned are. So the first ingredient I mentioned is the theory of Chen's theory of iterated integrals. So what are these? These are a way to construct differential forms and mapping spaces. And this theory of Chen's has applications to many parts of algebraic topology. It has applications to Lie theory, to the theory of multiple zeta values, and I think it's a beautiful theory. And I'll tell you the way in which this enters in this story. So let me just tell you briefly how Chen's construction of differential forms and mapping spaces works. So suppose we're interested in constructed differential forms on a path space. So I will consider the path space of a manifold as a path space. And if I have this path space, there is a tautological map, which is an evaluation map from a simplex of dimension k times the path space of this manifold to k copies of M, right? Which it just takes, well, k possible times and a path, and it maps it to, well, the path evaluated at those times. Right. So this is completely tautological. And so you can look at the corresponding map at the level of differential forms. So if you do the evaluation pullback, it gives you a map from, well, it goes in the other direction, differential forms in MK to differential forms in the simplex times the path space of M. Now, differential forms to the power K contains a copy of the kth power of differential forms on M. And here you have a push-forward map, which is integration along the simplex. And this is differential forms in the path space. So if you follow this composition, you take k differential forms, you view it as a differential form on m to the power k, then you apply the map induced by the evaluation map, and then you integrate over delta k, you get a map, and this map is Chen's map. So this is completely tautological. And this is something that you would have, that you can sort of mimic for any kind of mapping spaces. So it's a very tautological way of constructing differential forms on mapping spaces. Now, as I said before, well, this enters in this story in Gugenheim's the Rham theorem. So let me tell you what this is. The problem is the following: the Rham theorem, the usual statement that singular cohomology is isomorphic to the Rham cohomology, is proven by just taking a differential form and integrating it over a simplex. And that gives you a linear map, which induces an isomorphism in cohomology from differential forms to singular cochains. And that's fine. But this map has a peculiar property, and the property it has is that it is not an algebra map, but it induces an algebra map in cohomology. And that's not a very natural situation, right? You have a linear map, which is not an algebra map, but it somehow induces an isomorphism in cohomology. So this begs for a better explanation, and the better explanation was given by Gugenheim, which proved the following theorem. He proved that, in fact, the Rham's map is just the first order term in an infinite sequence of maps that give an A-infinity equivalence between the algebra of differential forms in G and the algebra of singular cochains. But I'm sorry, from the algebra of singular of differential forms on M to the algebra of singular cochains in M. So this is an answer to the question I stated before, is that the reason why it actually induces an isomorphism in cohomology of rings, which even if it's not a morphism of algebras, is just because it's the first step of an A-infinity morphism. So this is the theorem of Gugenheim. Now, this theorem of Gugenheim is better than what I'm stating. It doesn't only prove that there exists such a map, it constructs the map explicitly. So this map is constructed as follows. Let me just give you a formula for this map. So if it is an A-infinity map, what it does, it should start with k copies of differential forms, and somehow out of this produce singular cochain on M. That's the kind of thing you need to produce whenever you're going to construct an A-infinity map. And the formula is very explicit. It uses some combinatorial piece of data, which is, I will call it theta k, which is some combinatorial map that I think Manuel knows well. And this is a map from a cube of dimension k minus 1 to the path space of a simplex of dimension k. And this is simply a piecewise linear map. Some explicit formulas that I don't have time to write down, but notice that having a map from the k minus 1 dimensional cube to the path space of the simplex, it is the same thing as having a map from a k dimensional cube to a k dimensional simplex. So it's some way of folding a cube onto a simplex. That's what this combinatorial map is. Anyway, once you fix this combinatorial map with some properties, you can write down a formula for Gugenheim's map. And Gugenheim's map is given as follows. You have k differential forms. And what it does is the following. First, you apply Chen's iterated integrals to alpha 1 alpha k. What that gives you is a differential form on the path space of M. Then you apply the pullback by the path map associated to sigma. So that gives you a differential form on the path space of the simplex. And then you apply theta k pullback, and that gives you a differential form on the cube and you integrate over the cube. So this is completely very explicit formula. I wanted to write it down because, well, because I like it. So it not only does it say there exists some map, but it produces a very explicit map in terms of Chen's iterated integrals. But this is the theorem that Gugenheim proved. Now, the way in which this constructor enters the proof of the statement I'm talking about is as follows. It relates to the cohomology of classifying spaces. So let me show you. The next ingredient, which is the Bott-Shulman-Stasheff algebra of a Lie group G. So it means that it is the following here. G is a Lie group, and if you have a Lie group, you can construct what's called the Bott-Shulman-Stasheff algebra of this Lie group, which is just the algebra of differential forms on copies of G, right? So you consider an algebra which is, say, generated by things like this, sum over Q and P of differential forms on P copies of G. If you sum over these things, it turns out this space, well, it is a chain complex because it's a double complex like this, where the vertical differential is given by the Rham's operator and the horizontal differential is given by the simplicial structure. And not only is it a chain complex, but it's actually a DG algebra. So this is a DG algebra, which I will denote by differential forms on PG. Now this DG algebra behaves, as the notation suggests, this behaves as differential forms on the classifying space of G. In particular, its cohomology is that of PG. So this is just one of the possible models that you have for computing the cohomology of the classifying space of a Lie group, or in general, the classifying space of a simplicial manifold. So this is this Bott-Shulman-Stasheff algebra. Now, the way in which this theorem of Gugenheim enters is because one can produce a version of the infinity de Rham theorem for classifying spaces, and it's the following theorem that we proved with Alex, which is that if you consider this Bott-Shulman-Stasheff algebra of G, then you can produce an A-infinity map, an A-infinity quasi-isomorphism from this Bott-Shulman-Stasheff algebra to the algebra of Hochschild cochains on the algebra of singular chains on G. So both of these spaces are known to compute the cohomology of PG. So there are two different models for the cohomology of PG. But here what we produce is an explicit A-infinity quasi-isomorphism between them. And this A-infinity quasi-isomorphism between them uses, well, the formula of Gugenheim. So it's the same, well, it's a similar formula where you use iterated integrals plus the simplicial structure. So you can think of this as a version of the.
Camilo, I have a question.
Yes.
Can I ask a question?
Yes.
So this A-infinity quasi-isomorphism, there are no conditions on the connectivity of G here.
No.
No.
I think not.
Right.
No, this is for G arbitrary.
Okay.
Yeah,
So,
I think we don't use any. Yeah, there's
and
no
one more
assumption.
comment, sorry, is that we usually stop at 12:20 to have time for questions.
All right. And what time is it?
12:15.
All right. So I will finish soon. Okay, good. All right. So there is an infinity quasi-isomorphism in this way, and the way in which this enters. All right. So why is this relevant? Is because of this diagram I showed you here when I wrote this map. Is because this intermediate category B uses this Bott-Shulman-Stasheff algebra. So when you want to compute, to compare the corresponding DG categories, you need to compare the corresponding mapping spaces, and the mapping spaces here are defined in terms of the Bott-Shulman category, and the mapping spaces here are defined in terms of Hochschild complexes, and that's why you need an infinity morphisms between them. That's where this enters the proof. Now, the other statement that I wanted to mention is the other piece of information that enters is the fact that this algebra of differential forms on BG is not a commutative algebra. And it is not a commutative algebra because the cut product is not commutative, right? So this this behaves as differential forms on BG, except that it's non-commutative. And so Chern-Weil theory usually works for commutative algebras. So if you want to apply to this setting, you need a non-commutative version of Chern-Weil theory, and that's where we use the construction of Alekseev-Meinrenken. That's where it enters. All right, so now I want to briefly mention how this theorem relates to, so far, as a summary, I've shown you how you can prove that this category, this is equivalent, infinity equivalent to this category mod of C of G. Right, that's what I've said so far. Now, I want to explain how this is related to the theory of local systems on classifying spaces. So what do I mean by local systems? There are several possible definitions. First definition is from the point of view of differential geometry as superconnections on a manifold. That's one way to define a local system. You can also define it from the point of view of representation theory as representations, infinity representations of the infinity groupoid of a manifold. Or you can, from the point of view of homotopy theory, view them as modules over the algebra of singular chains on the base loop space of the manifold. Now, I want to say something about this, although maybe with this audience it's not necessary, but of course, the base loop space is not an associative monoid because, well, different ways of composing gives you different parametrizations of the interval, but it wants to be a group. And the way to correct this is by remembering the length of the interval. In this way, you can construct the Moore loop space of a space, and this Moore loop space is somehow a correction for this lack of associativity, and it does behave as a monoid. So that's a monoid that's used in the definition of high local systems. So one way of defining local systems in this sort of infinity way is defining them as modules over the algebra of singular chains on the Moore loop space of a space. So these are three possible ways of defining infinity local systems. And of course, the point is that all these ways of defining local systems are equivalent. So you can think of local systems as superconnections, you can think of them as representations of the infinity groupoid, or you can think of them as modules over the algebra of singular chains on the Moore loop space. These are three different ways of thinking about local systems. Each of them you can organize into a DG category, and the resulting DG categories are equivalent. So you have a sort of a well-defined theory of local systems on spaces in this way. This is work with Locke and Smith. They proved something that it's sometimes called the higher Riemann-Hilbert correspondence. Holstein proved some other instances, and Florian Schetz and I proved some other parts. We will abuse the notation and call log X for any of these categories. Now, the theorem I want to mention, this theorem has a star, and the reason it has a star is because the other theorems I mentioned before, they are already written up. So the first one is already on the archive. The second one will be on the archive in the next few weeks. This one will take a couple of months. So that's why it has a star, because we haven't written everything down, but I think we have a proof. And the theorem is the following, is that if you have a compact Lie group, which is simply connected, then these categories that I described before, the category rep of TG as a DG category, category of modules over C of G as a DG category, and the category of local systems on BG, they're all equivalent. So it means that these categories of modules that I described, they admit a topological interpretation as categories of local systems on the classifying space of G. So from this point of view, the construction that I explained is a categorification of the Chern-Weil theory, right? So Chern-Weil theory produces an infinitesimal description of the cohomology of the classifying space, and this produces an infinitesimal description of a different invariant, which is a category of local systems on the space BG. And there's a corresponding Chern-Weil functor which categorifies the Chern-Weil homomorphism, and things behaves the way the way you expect. Okay, so let me just finish by giving you two examples of how this works. So, well, what does this say in the simplest possible case, right? So I'm saying that this category of local systems is the same as modules over chains in G and the same as representations of DG. So in particular, when you look at the endomorphisms of the trivial module, then you should get on the one side here, you get the endomorphisms in this category, and this is well, the Hochschild cohomology of this algebra of singular chains in G, and this is the invariant polynomials in the Lie algebra. And these both are the cohomology with the trivial local system of BG, right? So in this way, when you apply this equivalence of categories to a trivial module, you recover, well, the computation of the cohomology of BG for the trivial local system. But the point is that you can have more interesting local systems on BG. And this is the other example I want to mention. When you have a loop space, when you have a sort of any space, but in this case BG, you can consider the loop space vibration, which goes from the loop space of BG to BG. And because you have this loop space vibration, you have a Gauss-Manin connection for this vibration. And if you follow through the identifications, you'll check that this Gauss-Manin connection corresponds to a very specific representation of this differential graded Lie algebra, which is the Chern-Weil-Eilenberg complex of it. And so if you believe the theorem, then the theorem predicts that the following is true, that the cohomology of the total space of this vibration, which is the loop space of BG, is the maps in this DG category from the trivial module to this local system, and should also be the maps from, in this category, from the trivial module to that local system. But what is this? Or rather, what is this? This is the cohomology, the Hochschild cohomology of singular chains in G with values in this module. And this is the equivariant cohomology. This is the equivariant cohomology. Of G acting on itself by conjugation. And indeed, it is known to be the case that if you compute the equivariant cohomology of G acting on itself by conjugation, what you compute is the cohomology of the loop space of BG, right? So it means that the Chern-Weil theory can now be extended to more general local systems. So BG in particular for the Gauss-Manin local system associated to the loop space vibration on BG, you recover this fact that the equivariant cohomology of the conjugation action on G on itself is isomorphic to the cohomology of the loop space of BG. So you recover sort of computations that were already known. But yeah, there are other examples that one can mention, but I think this is a good place to stop. So thank you.
Okay, so I think we can clap. Are there any questions for Camilo?
I have one question. It's in that last theorem with the star, the last two items where you have local systems on BG and DG modules over chains on G.
Right.
Is that a special case of, one knows that infinity local systems on any space is the same as DG modules over the chains on the base loop space.
Right.
So if you choose the space to be BG, wouldn't that show the equivalence of the last two items?
That's right. Yeah, I should be more precise. So I think one could, in principle, yes, thank you for the question. So, if I understand your comment, I think you're referring to the fact that the base loop space on BG is homotopy equivalent to G, and so chains here are the same as chains there. That's right. Yeah. So yeah, that would be sort of an abstract reason to believe, except that I'm sort of taking very specific kinds of modules, as I said before. So this is sort of the abstract reason why it's true. But then if you want to specify the sufficiently smooth modules, then you restrict to some smaller category of this, and you want to make sure that that it actually coincides. Okay. Now, the way I want to construct it is by constructing this classifying space as a limit of manifolds and using the Chern-Weil functor, and then making it sort of commute with the limit, and then that would be sort of a way of doing it. But it's because when I say mod here, I'm hiding always an ambiguity, which is I'm specifying a very specific kind of smooth modules, and that's why there's something to be proved. But I think you're completely right that this is sort of the reason why this should be true.
So does this mean that in terms of the homotopy theory of these categories, the smoothness is not playing any role?
That's right, yeah. So I think I think in a sense, it's like saying that if you look at smooth things, they're sort of dense. They generate everything, exactly. Which you can sort of approximate things by smooth. I see. By smooth representation. Yeah, that's sort of the point. That's
one thing that I like is that you have this, it's not even contractive, it's even acyclic, this TG. So it's like 0. And its representations is quite rich.
That's right,
so it's not a quasi-isomorphism invariant taking representations of something.
Exactly, yeah. You start with something contractive, but still it contains information. And one possible objection or worry that I had was that maybe because TG is contractible, maybe you get very silly representations, right? Maybe this is not an interesting theory because you don't have enough examples, but it turns out that you have a functor from TG. Well, G is a subalgebra of TG. So you have a restriction functor from rep of TG to rep of G. And it turns out that this functor has a left adjoint. And this left, so it means that you can also go in the other direction. So given any representation of G, you can construct a representation of TG. So you have, let me write it here. Given any representation of G, you can produce a representation of TG by some adjoint functor to the inclusion. And so it means that you have at least as many examples as you have representations of G. So it really contains the theory via this inclusion functor. So it's not, you do get interesting examples, at least as many as representations of G. That's right.
Are there any more questions for Camilo?
Yes, I have 2 questions, if I may ask. One question is regarding the compactness assumption. You said something about Chern-Weil isomorphism, but if you work over complex numbers, it also works for complex semi-simple, which is not compact necessarily.
All right.
Is compactness used anywhere essentially, yes, or it's just Chern-Weil isomorphism?
No, compactness is used essentially in the proof, and I can tell you where. It's in the following place. I said that we use this Bott-Shulman algebra, which is differential forms on G, which as a vector space is just the sum of differential forms on Q forms on GP, right? So this is this space. Mm-hmm. Now this model computes the cohomology of BG. But what we really need in one of the steps of the proof is to restrict this algebra to a smaller subalgebra, which is a subalgebra of invariant with respect to, in some specific way, but a subalgebra of things which are invariant with respect to G, or indeed to respect to copies of G. So inside of this Bott-Shulman algebra, you construct a smaller subalgebra, which is the subalgebra of invariant things in a sense, in a sense that I don't have time to specify. And now, if you want to make sure that this subalgebra computes the same cohomology of PG, so that it still works as a model for the cohomology of PG. Well, you're using the fact that when you restrict to invariant things, you get the cohomology doesn't change, and there we use compactness because then you can integrate.
I see.
That's where it enters. So I'm not sure if you're but I'm not sure. You say that maybe it's true in more general sort of semi-simple case. I'm not. We haven't thought about it. I don't know the answer, but definitely we're using compactness in this step.
I see. And quick question. Is there an analog of this representation of the TG for Lie groupoids?
Right. So let me see. So I guess the first question. Well, I've thought about, okay, so I think one can in principle define, if you have a Lie, well, then you need to worry about a Lie algebroid, right? And then of course, if you have a Lie algebroid, it still makes sense to have sort of an action by Lie derivatives and contractions. Mm-hmm. But once you sort of do a theory like this, it becomes less clear what a basic subspace of a DG space should be, because these Lie derivatives and contractions, if you're working in the case of a Lie algebroid, you should. The problem is the following: you have Lie derivatives and contractions where now X is a section of the Lie algebroid, so it means that X can be multiplied by a function, and the problem is that the Lie derivative is not linear with respect to functions. So if you force the thing to be invariant with respect to contractions and Lie derivatives for any section, the fact that this is not linear with respect to modules gives you too strict a restriction. So, well, I once thought about a problem similar to this, and that's the place where I got stuck, but I don't know the answer. Okay. So what I can say is that when I tried something like this, there was something I couldn't fix, which is the fact that because this is non-linear on functions, then you don't get a good notion of invariant. Well, that's one way of saying it. Yeah.
Okay, thanks.
Yeah. So another way of answering the same question probably is that there's no analog of the Weil model for equivariant cohomology for Lie groupoids, right? Precisely because there's no good notion of being basic. So you have a model for the Weil algebra, but once you try to pass to the basic part, which would be differential forms from BG, it doesn't make sense. There's no way of doing that, as far as I can tell.
Okay, so let's thank Camilo again.
Thank you. Thanks.
Let me stop the recording.